Hi, I'm Vivek.
I'm Tarun.
And I'm Sayan.
In this project, we are doing a comparative study of bubble growth dynamics problem using DeepONets. We also perform a systematic and comparative study comparing DeepONet with LSTMs, GRUs, and sequence models. We use DeepONets that works on the universal operator approximation theorem and uses this to learn the underlying operator behind the given dataset. We analyze the generalization capability or the extrapolation capability of DeepONet, and we compare it with LSTM, GRE, and sequence model. We also compare the training speed of the above mentioned models. In this problem, the governing equation is the Rayleigh-Plesset equation that is derived from the Navier-Stokes equation, a momentum conservation equation. So what this does is the problem setup can be described as a channel containing a bubble in a fluid. This fluid, the ambient fluid, is subjected to a pressure fluctuation. So under such situation, how will the bubble radius respond? So this is how it actually responds. Suppose the green curve is the pressure fluctuation imposed on the fluid. The bubble radius will follow this curve. If you see clearly, each of these green, blue, and orange curves have two time scales, a low frequency component and a high frequency component. This bubble radius can be obtained by solving the Rayleigh-Plesset equation. For this purpose, we need to generate the data. As you see, the pressure field is continuous and radius is continuous, but when you feed it to a neural network model, we need to discretize it. So for generating the data, we have used finite difference method for generating the good quality, high resolution data. So using finite difference method, we use the scipy.integrate.solve IVP package available in Python for discretizing and doing finite difference simulations for the previously mentioned Rayleigh-Plesset equation. We estimate the variation in bubble radius as a function of time, as mentioned before, for a given random pressure fluctuation. Now, this random pressure fluctuation is sampled from a Gaussian random field. The length scale of the Gaussian random field is varied for different data sets. Next, what is DeepONet? DeepONet stands for the Deep Operator Networks. It's a neural network model that enables us to learn the operators behind the problem. So for a given data set, unlike LSTM or GRE or sequence model that try to directly approximate the function, which is essentially a mapping from a real space to another real space. Deep operator networks try to approximate the operator, which is a mapping from one function space to another function space. In this case, it is a mapping from the pressure function space to the radius function space. So this operator is being approximated by the deep operator networks. So the DeepONet consists of two networks, the branch network and the trunk network. In this problem, we feed the pressure data as input to the branch network. Here, M stands for the number of sensor points or the sensor resolution. T, the time, is fed as input to the trunk network. Here, a kind of dot product is being performed, and we will be obtaining the radius as a function of time T, this time T, as the output of the DeepONet. So for this problem, the architecture we used is for both branch net and the trunk net, we have 5 hidden layers, fully connected dense layers. We use ReLU activation, and there are 100 neurons in each of these 5 hidden layers.
So we have compared GRU and LSTMs. LSTM and GRU have gated mechanism, which makes them efficient to remember stuff from historical data, unlike RNNs. So LSTMs or GRUs are better in that sort. GRU is especially better than LSTMs because they are efficient performatively, because they don't maintain cell state, and they take care of this mechanism by using reset gate and update gate. For our experiment, we have performed this experiment with 50 GRE units with dense layer with variant output dimensions. These variant output dimensions are proportional to M, which are basically a sensor dimension. We have also used sequence to sequence architecture. So sequence and sequence architecture is, again, good in time series modeling, but they're different in the architecture where they're general purpose encoder decoder framework. Essentially, they take the entire state of from the encoder and it's directly passed to the decoder, and thereby retaining past information better than LSTM and GRUs. So this is how a sequence and sequence architecture looks like, where you have an explicit encoder and explicit decoder. We have used GRUs from Kara's library with 20 units as encoder and 20 units in decoder. We then use states returned from the encoder and feeding that information to our decoder, and the output from the decoder is then fed into a dense layer with varying output dimension, which is again M. So what did we exactly do and how our experimental setup looks like? We performed 2 experiments. One is sensitivity to sensor resolution, where we have compared in M equals to 20, 80, and 200. We test how well the model fits the truth graph, essentially. And the other experiment that we did is basically generalization capability over different data distribution on various Gaussian random field length scale. As you can see in the slide, it starts from 0.07 and goes to 0.8.
All right. So since we now have an understanding about the problem we need to solve, which is predicting how the radius of a bubble varies in a fluid, and we also have our 4 models, we can now perform a comparative study over the experiments we just discussed. So let us see how these 3 architectures compare against each other. The first graph that we draw out is a prediction versus truth plot. Here we can see how a DeepONet, a GRU, a sequence-to-sequence model differ from each other in trying to fit the truth plot over various sensor resolutions. Focusing on the M is equal to 20, which is a sparse data category, since there are very less number of sensors in this case, it shows how low the generalization error for DeepONet is. Here we can see the DeepONet function, which is the blue line, fits very closely to the truth function, which is the orange line. Whereas in the case of the sequence-to-sequence model, the blue line is just barely fitting the yellow line. This is the extrapolation graph of the DeepONet over varying length scales from the Gaussian random field and how the mean square error varies with it. Here, the training data we consider is of length scale 10 power minus 1 or 0.1, and hence it has the lowest mean square error. But we also observe that the DeepONet has a very low mean square error for different length scales too. So here we create a GIF that shows how our DeepONet learns. We can see that the DeepONet first fits the low frequency components of our function, and then over many epochs starts fitting the higher frequency component. When we reach to about a 25,000 epoch mark, we see that the DeepONet is already doing a pretty good job in trying to fit the truth curve. This GIF goes on till 50,000 epochs, but we have actually trained it for 100,000 epochs, which is the curve shown a few slides before. Here is a chart which shows us the training time difference between DeepONet, LSTMs, GRUs, and the sequence-to-sequence models. The advantage of using a DeepONet is both the subnetworks, the branch net, and the trunk net are dense layers and hence can be parallelized easily. However, in the case of an LSTM, a GRU, or a sequence-to-sequence model, each hidden state in such a model is dependent on the temporal time states leading up to it. For this reason, it is not easy to parallelize an LSTM, GRU, or sequence-to-sequence model, and which results in very high training times for such models. Here, the training time for the DeepONet is just about 60 seconds for 1,000 epochs, whereas the training time for LSTMs, sequence is more than 450 seconds for the same amount of epochs. So based on these experiments and the plots that we just showed, we can draw out certain conclusions. The first massive takeaway is that since the DeepONet approximates operators and is not a functional approximator, it is able to fit the truth curve even for very small sensor resolutions, as we saw in the case of just 20. The DeepONet is much faster to train as compared to GRU and sequence-to-sequence. And this is because the DeepONet can be parallelized easily when compared to the GRU and sequence-to-sequence models. That ends our video presentation of our project. Thank you.